You guys want to go? Somewhere outside would be nice.
Yeah, exactly.
No
opinion.
We go to Timber Plus?
It's fine.
Somewhere close. Somewhere
close.
Close is okay, but if people want to come from NTU, this is not close. It's a nice outing. Please come. We can have a few snacks and snaps if you're interested. And we'll probably have another party which you won't be part of, but at the end of this month, because I think a couple of team members are leaving. So let's see how it goes. So CJ and Beatrice are both leaving at the end of the month. CJ is here. Have you announced already? Not yet. Okay. So we require you to give a presentation, sharing your time with us and, how things are going. I'll ask Beatrice for the same. So we can do something where maybe after Tuesday group meeting, we can go down to Max. I think as we always do, tradition. All right. That'll be fun to do. Did Chiran give a presentation? No, right? I think he just escaped. I will ask him. I will ask him to come. We'll have something at the end of September, maybe, before you guys leave. But yeah, tomorrow's casual, so please join. I'll put it on Clouded Leopard once it's decided, around 6 p.m. You can start earlier if you want, but I have a meeting from 4 to 6. So as soon as I'm done, I will join. Please come and we can sit down and chit chat. Yeah. That's one announcement. Apart from that, I think nothing else. Oh, there's one more for the IMRI folks. We are burning through our OOE very fast, which is a good thing. I'm not worried too much about it, but please be a little judicious in using it. Just think about it twice instead of not thinking about it. That's all I'll say. We brought forward the balanced budget from next year to this year. I can give you the numbers. Let me see. So, give me a second. Where is it? Okay, so we have already spent 71,000. We spent 155,000 this year. Okay. And now we have 100,000 left, approximately. 130,000, something like this. 130,000. So it's not a lot. So I would advise you to, I don't know, think through or order in advance. That's fine. First come, first serve. And then have everything that you need. So please plan accordingly. I mean, at this point in IMRI, there's only, I think, Pablo's, Jace, Pawan, Mahesh, right? That's it. There's only 4 of you, so it should be okay. And Bala. Okay, just let you know. Other thing to do would be don't worry so much because the Match GD project is also funded at NTU. We have other funds in NTU. So worst case, we can also start to supplement next year through the project in NTU. Okay, so it's nothing to be crazily worried about, but just something to be wary about. I wanted to bring that up. Apart from that, I don't have any more announcements. Over to you, Martin.
Yes. His name is Martin, and I am a PhD student at the Technical University of Denmark, handing in my thesis end of this month. So almost done. And I will quickly go through what I've been doing on the computational investigation and generation of disordered materials. So in reality, we like to consider disordered and functional materials because it enhances the functional property. In reality, when we begin to introduce dopants into materials such as the battery cathodes, then we begin enhancing both their capacity, voltage, but also their stability. And this disorder comes in many forms. There is something where you have a substitutional disorder, where you take either a large or smaller atom and replace it by the atom which is currently there in the whole structure. You can also have you can also remove the atom completely, creating a vacancy. And there's also other disorders, but these two types, substitutional and vacancy disorder, is what I'm mostly focusing on. This is called site disorder. And the way we visualize this in crystal structures is by partial occupancy, where the symmetry sites in the crystal, you will see that the symmetry site is partially occupied by different elements or vacancies in void and reality.
So are there any data points in ICSD that are interstitial or substitutional?
Yeah, we are looking into that, but in reality, we will try to neglect it because, as I've discussed with Hyman, and also Shanghai and Huan, is that this might be need a stable structures which we cannot rely on.
Okay.
So yeah. So mostly what is an ISD is substitutional and vacancy site disorder, and reality just site disorder. And the way we consider this partial occupancy is like different elements, so it's like different pieces of cakes. The issue is because of the inherent static nature of how these elements are occupied, simulating them is not really a piece of cake in reality. I don't know how many of you know about batteries, but also I'll just quickly brief through because that's what my most I've been focusing on. And a battery comes in many forms. There's three different parts of the battery: anode, electrolyte, and a cathode. I'm mostly focused on the cathode side of a battery. And for sodium-ion batteries, which I mostly look at, there's many different types of batteries. But I'm mostly focused on the polyionic type. Reason for this is that they show quite high stability and high voltage compared to the other groups, but they lack in ion conductivity and electronic conductivity, which we hope this order will sort of enhance in the long run. So for that reason, I've been considering quite a lot this phase space here, where I have 4 different crystalline structures, a lot of different anions, and a lot of different cations. And looking at this huge phase space, it's not possible with FT alone. Even machine learning interatomic potential will also be a bit of an issue. So in the end, one needs to go to computational generative models. But going there, we need to first go step by step, first going through the DFT, how much we can do, then do some machine learning guide search, and then we can do computational generative models in the end. And the ones that I've mostly been focusing on 3 different crystalline types, 3 different polyanions, and 4 different cations, creating a phase space which looks like this, where I have 3 different crystallines, and 4 different crystallines where I have sodium phosphate, olivine americite, sodium silicate, and sodium sulfur. And then I have sufficient metal ions considered iron, manganese, nickel, and cobalt. And in reality, what we are interested in is to look at different properties within this phase space. I am mostly considering looking at what is called the convex hull, which we use to identify if a certain material is stable or possible stable or not. And the way you look at these convex hull for a battery perspective is by basically discharging the cathodes. So we remove all the sodium. When all the sodium is removed, you have a charged battery. When it's all in there, it's a discharged battery. We need to simulate this whole process to see if there are any phase transition happening when we begin charging and discharging the battery.
Does the structure change in the battery?
Yes, but based on this, like if you have a phase transition here, it like this will mostly probe compositional disorder, but it can also lead to structural disorder.
In the sodium-ion batteries, does it become fully alloyed at any stage?
In reality, when it's fully disordered, it's an alloy. Yeah.
Yeah, but does it ever get to fully disordered phase in reality, or is it still crystalline?
Alloy, that's what we're aiming for, right? Because if we can remove all the sodium, so it's only in this case iron phosphate, then we're happy because then we utilize the battery as much as possible. Some does not like it. For example, for lead oxide, this is a very stable polyanions, are very stable, very little structural disorder. But for all layered oxides, you don't want to remove all the sodium because then you will in reality break the crystal. Yeah. But we mostly want to consider these static properties to see if there's any phase transitioning, because from the convex hull we can also get the voltage profile. But we are also interested in looking at the dynamics. So how does the sodium actually move? Reality modeling ionic conductivity. And we do this through molecular dynamics simulation. One can use other methods as well, but I've mostly been focusing on molecular dynamics simulation because it gives us a direct view of how the battery will move in the material.
And you can use these curves to do ionic conductivity calculation?
Yes, you use this together with the Einstein-Boltzmann's equation to get how much the diffusivity is for the sodium. You cannot get the electronic conductivity from this.
Yeah. Why is it fluctuating so much?
That's because of the thermostat. It has not equilibrated yet, but it does fluctuate a bit, especially in the beginning. And actually, in general, it does fluctuate a bit. It depends on what thermostat you use. If you force it too much to be a certain temperature, you bias. Yeah, what you say, you really limit the sodium movement quite a lot. While if you let it like fluctuate around a certain temperature, you more simulate how the sodium should move. Yeah. But the idea is to take all these two properties, like the stability and the ionic conductivity, and compare them directly to experimental plots. This is the voltage profile given by the sodium iron phosphate. And what we notice is that there is actually phase transitioning happening in this voltage profile. And it happens at 2/3 of sodium concentration in this material. But as you can see up in the convex hull, I find a phase at 0.5. Meaning that in reality, I did not capture this phase accurately. This is because I am considering very discretized concentration of sodium because I'm only considering a unit cell. So to really model this accurately, we need to go to much larger supercells with more atoms, and that DFT cannot calculate in the end. So that's why we need to use external methods such as machine learning interatomic potentials.
So we remove sodium ion from cathode anode and then move them.
Yeah, I move them slowly. Yeah,
by applying potential. By applying potential.
Oh, I don't apply external potential much. It's just that this is at 0 Kelvin, the convex hull.
How are you taking out? You already bonded them to this crystal structure.
I can just take them out. Then we create a vacancy, and then it's
some energy.
Huh?
You need some energy to take it out from the structure.
Yeah. But I can manually just say, hey, remove, and then look at what the energy is that specific. So that's why I cannot do the continuous movement because I don't have this external potential. If you want to have the continuous way of doing it, one need a very big supercell, then you need to look at the surface between the electrolyte and the cathodes. And that is really not possible with DFT.
You're taking some percent, like more than. Taking just some percent of sodium ion, right?
Yeah, I take one sodium out at a time.
Yeah.
Right. So right now there's 4 different sodiums. That's why there's 5 different possibilities in reality.
One atom, 1 ion per time.
Yeah. Yes. And that, but we need to do more. That's why we need supercells, and that's why we need these machine learning potentials.
And the structure broken, like if you take instead of 1, if you take 2, the structure still not stabilized.
Yeah, that's why it's very nice with these materials. It's okay if they're not stabilized, then we can just model this phase transition even further, right? But polyanions are very stabilized. So even if you remove all the sodium, it will not break the crystal. Yeah.
Even like I think the point is even at x is equal to 0, where you have one possibility, in a way the crystal doesn't break.
Yeah.
That's the crazy thing.
Yeah.
It's crazy.
Is it the ionic bond or valence bond?
Yeah, so when I remove sodium, the charge goes to the transition line.
How they bond it? Is the valence bond or ionic bond between the sodium and transition line?
I mean, the sodium doesn't bond with it.
It doesn't bond.
No.
I mean, or at least it is ionic, that's great, right? So
yeah,
what happens is these are intercalation areas, right? So that's
like the lithium.
Crystal has a phase.
Yeah, so no bonding, right?
In reality, it is no bonding.
What's bonding?
There's a little like there is bonding, but
it's just going in the void place.
Yeah,
something like that.
I actually don't have it here, but I also have done elastic band calculations where you move one sodium from the position to a vacancy position, where you actually can see how what energy it costs to go from A to B, and it's you might tell me I have not included the cut, but it's around 0.3 eV at 0 Kelvin.
Yeah. Here's another way to ask this question would be if you just did the transition metal SiO4.
Yeah.
If you just remove the purple atoms, would the structure be the same, or would there be slight differences?
If I remove
The purple atoms, the sodium.
the sodium, yeah. If I remove all the sodium, the structure will not differ.
Okay, that's the interesting bit.
Like
So this is more like
The volume
Space filling.
will cause change, but the structure itself will not breaking. It is what, yeah.
The same with the lithium conductors.
It's not bonding, it's just singular, like.
No, there's no direct bonding. It's yeah.
But just also curiosity, whenever integration and deintegration happens, there will be some stress on the ladder and it get removed, right?
Yeah, the voltage stress directly. So the volume will change, but it's not, yeah.
Does this stress have some effect on the band gap or anything?
Then I have that set. Maybe it does. I can look at it. It's not change a lot on the band gap. Yeah, it is. But
The crystal actually change that, right?
yeah, that will be doing. I've not tested it, but my hypothesis would be it will not change a lot.
Question to the peroxide guys, like the A side is also 6 If you remove some of the A side, does the peroxide start to break?
But it's still bonding. It is not bonding that time. No, it's a bonding, there's a bond there. There's a bond, that's why I asked if bonding was just line on the white space.
No, nothing.
Is that right? So it has B actually.
Why putting NA to put NaX, right? The only number of putting them one side, right? Depends on the volume depth in the volume space, right? Why you want to put NA there?
No, you have to balance the chart. So
Yeah.
We can put either
Now to
lithium
go to the-
or sodium. Right?
that much sodium is inserted into the
SO4 is
structure.
-2, right? What is transition metal using here?
That's the one down there. Iron, manganese, nickel, and cobalt. So they all go to 2 from 2 plus to 3 plus when I remove sodium.
There is some minimal bonding.
It's full from +2 +3.
2 plus 2 plus 3.
That means the sodium is removed, so someone has to give an extra charge. So you have to have.
Positive not. Transition is +2, right? So you got to have +4. And it's SO4 is -2.
No,
Do you have a partial density of states of the band structure?
no, but I will get.
Okay. I mean, you could easily do it.
Yeah,
but-
it's easy.
So, like, for example, are the bonding orbitals mostly coming from the transition metals? I'm guessing the valence band edge is mostly,
Yeah.
3D states of the iron and the manganese.
Yeah.
And the sodium is,
Yeah.
there will be some contribution, but it'll be small. This is what I would get. That's what is happening. Physics wise speaking.
Like, still not that bad.
Why?
There is charge.
SO4 is
I'm going to use the restroom real quick. I'll be right back. Please continue.
Yeah, no, there is charge balance.
SO4 is
Oxygen is -2. Oxygen is -2. Phosphate is +5. It's four.
It's SO4. Okay, but it's in -8. What is sulfur vacancy here?
Huh?
What is sulfur, +2 or -2?
Sulfur is plus.
Why plus here?
It's +3, I think.
Then it should be minus, right?
No,
Sulfur.
it's normally plus.
So it's going toward chlorine and chlorine side, right? Then we have negative again.
No, sulfur is a plus. The same with you can see, just so I actually have it here, right? Here you can see what the total is. So PO4 is -3. And SO4 is -2.
Correct.
Yeah, so sulfur is,
Plastic.
Plus, okay, then go to next. Now, SO4 is -2, right? Transition metal is +2.
yeah.
Next slide. Then how is that balance?
If transition is -+2 and sodium is +1.
But they are two, not one.
Yeah, 1 to 1. So there's just as many. So here you can see you have where's my mouse here? -3, +2, and then +1 for sodium.
Yeah, but now you have for two.
If you have silicate, then you have -4.
-4.
Then you have 2 sodium and 1 transition metal line. I cannot remove all the sodium in silicate. That's true. Silicate is limited to only to remove half of sodium in the material. Silicate is 2 TM silicate O4.
Yeah, this is fine.
So I cannot
This is
remove.
perfectly fine.
Yeah.
When talking about Na2, Tm +4 -2.
I think that
This one,
Maybe that's
Yeah.
two here.
I have to say, I rounded this up. There's a little more sodium here, but
Even the transition metal is
there's 2 transition metal lines, there's 2 sodium.
+4 here, right?
Yeah.
and the sodium is plus 6.
See,
So it will be SO4, the whole two, like it's double of SO4. Right? That's how it will balance.
Yeah.
So,
So the SO4 needs to be there.
Yes. In the parentheses have two.
you can only remove sodium until charge balance have like we only consider 2 plus to 3 plus in resistance line. We only remove sodium until we reach that limit. When we reach that limit, we cannot remove more sodium.
Yeah.
Yeah.
So you can always add more. It doesn't need to be charge balanced. So this is the saturated limit of more sodium.
Yeah.
You don't need to be charge balanced,
Yeah,
No.
that is right.
right?
Yeah.
So it should only be charge balanced in the presence of some limit where there's not enough
Only
sodium.
the limit, yeah.
That's the point. You can always add more
And
sodium.
I think that reduced formula is wrong. I think that-
Yeah, the sulfur I rounded so that you're right. Maybe I should fix this. Yeah, the sulfur I rounded.
So
I have the actual one data on it, but yeah.
One sodium transition metal, the next one.
yeah.
Yeah.
I see. Yeah, because it's TN2.
Yeah.
Got it.
Machine learning potentials, that's where we came from.
Yeah.
So just a quick recap, I think you've seen this multiple times. You take crystal
There are a lot of people here who may not know.
Okay,
It's
and that's why
for an audience.
So you take a crystal structure like this, then you map it into a graph where the nodes are equal to the atoms and the edges between the node are equal to the interaction between the atoms. And then you take this graph representation of the crystal structure and put it into a graphical neural network. You put this together with the labels from DFT calculations, such as energy, forces, and stress. Then you take the labels and this graph representation, and then you train the graphical neural network. So in the end, when you have a fully trained graphical neural network, the only thing I will do is I will take a crystal structure, map it into a graph, pass it through the graphical neural network, and then it will spit out like this colorful graph from which I can predict atomic properties like energy, forces, and stress. From this, we can then run very big cells and molecular dynamics simulation for these very big cells. But you can see here that we could do it quite accurately. You can see the DFT here on the x-axis, and you have the machine learning predicted on the y-axis. And it's a one-to-one with a very little mean absolute error, both in energy and functions. This is DFT energy and machine learning energy. The machine learning energy, that's this model here. This have predicted the forces and energy for each of these steps in the transition and the molecular dynamic simulations. And then I compared it with DFT, did a single point DFT calculation in reality, and saw how accurate they were.
This is the total energy in the unit cell.
Total energy. Yeah. Total energy.
Total energy of all the atoms.
It's coming. Coming here. You can do this with, this is just an example saying that you can do a lot of different, you can do a lot of this, but there's a lot of different graphical networks where you can do this comparison. You can do something like InfinityNet, which can predict energy, forces, and stress. Maze, which can predict energy, forces, and stress. ChargeNet, which can predict energy, forces, stress, and magnetic moment, which is crucial to your question before, because through magnetic moment, we can actually indirectly interpret what the redox process of the transition metal lines are. So in reality, when the magnetic moment of the transition metal line changes, we know that the redox goes to this particular transition metal line. Yes?
Can I explain the energy graph? Why is so many?
Huh?
Total energy is scalar.
It's per atom. Yeah, I need to set per atom here. Yeah. There is the total energy. I just gave it down by number of atoms.
Where do all the data points come from is the question.
Oh, it comes from this simulation. It's a molecular dynamics simulation where I run and then I stop it for each way a molecular dynamics simulation works is to simulate
Steps.
the atoms as a function of time. And then for each time step I have, you can in principle stop you can just take this particular time step out and then do a single point DFT calculation to basically do the electronic convergence. And then you can get the DFT predicted energies for that. Yeah. It's the same MD run. I just like take certain snapshots from the MD run. For example, to stop it now. Boom. Oh, stop. No, too long. No. Yeah, now I stopped it. Perfect. Then in reality, I can take this particular configuration to single point DFT on this, and then compare. I have a direct comparison.
So this MD simulations is done when intercalation is happening in the simulation.
I don't force intercalation to happen. I have removed some of the sodium, and then the system itself probes intercalation.
I think the answer is the time scale for
Yeah.
intercalations and the length scale are much higher.
Yeah.
This is picosecond.
No, actually I ran it a nanosecond, but yeah.
Okay.
Yeah.
No, then.
Any advantage to running
What
that?
is the point of doing the transient? So I don't understand.
Why?
Like this is a timestamp of the crystal structure, something like that. Right?
Yeah.
And so when you do timestamp, there should be some variation in the structure.
Yeah.
So what is that variation? I'm just trying to get.
Yeah. Then you're right. In reality, what I want to simulate is the transition. Like I want the intercalation. So by modeling the intercalation with molecular dynamic simulation, I know what the ionic conductivity of these materials are.
Then
Yes.
That's why you need long time.
That's why I need long time. I need never. Huh?
7 is zero country.
No, I have 800.
Oh,
And we are why comparing the DFT and the
Yeah, but the thing is, molecular dynamic simulation works using thermostats. So you have a heat bath where in reality,
Language
all
balance.
the configuration should be in a certain temperature. But when you stop, even though I stop it, the only thing DFT does in this calculation is calculating the electronic structure. So it's still a certain temperature. But just look at the electronic structure. So through the von Oppenheimer approximation, we know that we just stop it directly, calculate the DFT, and then we know it still is in this time in this temperature regime. Yeah. The model, to answer Andy's question, the force field used here is my model, which is called CCANE, where in reality it predicts energy, force, stress, magnetic moment, and atomic charges. So instead of indirectly model the transition metal, the redox process of the transition metal ions through magnetic moment, I do it directly with atomic charges. So I know directly this is the charge here, this is the charge here. We also do partial charges.
I have a question about these machine learning potential. So these different versions that you're showing.
Yeah.
So they are basically that a neural network that is being trained or trained with a lot of different.
A lot of data. A lot of data, yeah.
Okay. So when you input your solid in a graph input, it doesn't need to. It has to be at like the structure that you want to calculate.
Yeah.
Like you won't do like in DFT normally like people do like that thing that where they like how do you call it? Relax the structure.
You can do relaxation of structures with these machine learning force fields.
Hmm.
But what this model does, there's two parts of DFT. One is called the self-consistent, or what is it? Yeah, SCF cycle. Self-consistent. Yeah. One part is where you first convert the electronic structures using quantum mechanics in reality. And then the other part of the DFT is ionic steps, where you move the ions a little bit. So you look at the electron and the ionic movement independently. And then you assume, because the velocities of the two are so different, that you can calculate that the electrons instantaneously converge when you move an ion. So what the machine learning force field does is calculating the electronic behavior. And then you move one with an optimizer, then again it calculates the electronic behavior and so on. So that's what the machine learning force fields are used for. It's for the getting the electronic convergence.
But just saying like the last two terms, the magnetic momentum and also atomic charge, is it like sort of correlated? With
They're directly correlated, yes.
Yeah.
The issue is that magnetic moment directly is in most DFT calculation have magnetic moment directly, while atomic charges you need to have the charge, like the electronic density, to get that. That's why nobody has done it. Not many people does it because there's not a lot of data. But I have a lot of data which I did it for. That's why I did it, because I have the data.
Okay, there will be a data study like how effective is it adding the atomic charge?
I did the check, and it didn't change the prediction that much. But the only thing it can be used for is identifying correctly where's the rate of process of the transition lines. Yeah.
I have a question. So all of these are trained, the three we know they're trained on different data sets, which is the trajectory data sets and so on.
Three of them here are trained on the materials project data set, and this one is trained on my data set.
Only on your data set.
Only my data set.
You don't have a CPANE version on OMAT 24.
Not yet. The issue is that in reality, the OMAP, like you can see now, NICFIP finally came out with theirs. It takes quite a lot of time and energy to really fine-tune this model, and I have had an attempt on it. But the issue is you really need to be careful when you do these things. There's a lot of things they don't really tell when you do these fine-tuning.
Well, how do you exactly include? So, like for example, we know that ChargeNet is based on a graph, and then MACE is based on ACE,
No,
the atomic cluster environment.
they're all based on graphs.
Right, all based on graphs, right?
Yeah,
So
they're all based on graphs. What MACE does,
Yeah.
different from these three, is it incorporate the idea of mapping the graph
Local
into
clusters.
different clusters.
Yeah. Aware. And then ChargeNet calculates the total charge.
Yeah.
So my question is, how do they include this in your model of the graph output?
Yeah.
Where do they include it?
I can explain. So in reality, you have nodes
Mhm.
and vectors.
Yeah.
To get the energy, you will have like this graphical linear. You have like this box here.
Yeah.
Then you pass through message passing. So
Mhm.
message, like in reality, you message around and then you update, and you have this graphical neural network. But
Yeah.
this is not where the magic happens.
Mhm.
The magic happens at the end layer where you have this
Mm.
MLP, a machine learning perceptron.
Yeah, multi-layer perceptron.
Yeah, and from that you pass through the node features, it's called.
Mhm.
When you pass it through that perceptron, you'll have a
Okay.
node vector,
Mhm.
and from that node vector in reality is just a sum. If you sum all the nodes in the end, you get the energy.
Okay.
To get the forces, you will take this node
Mm.
vector and then do a derivative using the atomic positions.
Mhm.
And the same with the stress.
I see.
For magnetic moment, ChargeNet
I
did something
see.
clever. They looked at the node vector and node features in the second to last layer of the machine of the message passing, like the graphical neural networks. Then they used that and directly from the node features predicted the magnetic moment.
I see.
So they hoped that indirectly this doing it by the second to last, that when you pass it back, it will enhance the performance. But in reality, because I have made this, I did the test, and in the paper I wrote, ChargeNet postulate, because they never showed that that's actually true. Yeah. Yes.
So you mean your models C-Lion can directly predict magnetic moment
Yes.
as the vector?
Yeah, just like ChargeNet. Yes. Other things have a scalar value.
No, actually, ChargeNet cannot predict magnetic moment as the vector.
No, only scalar value. The same.
Yeah.
Only scalar value.
So you can the vector and also,
Only scalar value.
yeah, only that.
Yes.
So the problem is, ChargeNet actually they get involved in the magnetic moment as a way to complete the wavelength state.
Yes.
So that's why it's called ChargeNet, not
Yeah.
magnet.
Exactly.
Exactly. So if you already have magnetic moment, why do you introduce the atomic charge? I think these two maybe.
Yeah, that's a good. It's a good question. The reason is that magnetic moment you can indirectly get the atomic charge. So it's just an indirect way of getting atomic charge. The reason why you use magnetic moment is because you don't have the atomic charge. Nobody calculates the atomic charge density, charge time. So when you don't have it, you use magnetic moment. But if you have it, you have the opinion, then you can just directly get it. There's no reason to do indirect.
But now you have it.
Yeah, then I can get it direct.
So is it just a bond summation?
It's the same idea. You do the same as we did with charge. We did the same as charge, just with atomic charges. So
the charges from all the nodes.
You also get it from the second last layer.
yeah, the same idea. The issue is that a code called, what is it, SpookyNet tried to do it directly, but then you need to give the atomic charge from the start of the calculation, and this is not good. You want to have it in. The only thing you want to give the graphical neural network is your
Set.
Yeah.
Is it what?
The
Crystal,
structure.
just the structure. The structure and the atomic types. That's what you want to give, nothing else.
Guys, I have a very stupid question to all the theory people there. Just wondering, like this MACE MP0, the DO is still in the archive. Means that it's still not given a peer review and all.
It's crazy. Yeah,
It's
but
probably
it's one of the
under-
most cited machine enforcement ever.
Yeah, that's what I'm trying to understand.
There are papers that are published that use this. It's probably under nature science. But it's really,
Yeah, I think so.
takes a year and a half, 2 years to get it published.
Electric don't have this.
They are.
Yeah.
They are.
In the way. In the
The
way.
thing is,
Arya is an author, right?
Agner is awful. The thing is,
His advisor. is-
everybody uses it, but the issue is that what they want, I think they have been too ambitious. That's why it's good to put it on archive. I think they have been too ambitious. So what they want is to show
Claim a foundation
they
model.
want to clean it so it's perfect. So they want to have a big paper saying this is, and they want to test it on a lot of different materials. I think they're too ambitious. That's why it takes so long. 2 years in reality, right?
Yeah, 2
They
years.
want to test it on every possible way.
Yeah.
And I know that Klaber, the one who is the professor behind all this, he is doing a very big benchmark right now because he really do not like mad bench discovery. So he's trying to show the mad bench discovery is not good.
Pointless. A question from Rico.
Yes. Maybe not. Here you go.
He had his hand up.
So, one, you get it. So you have a wrapping. Homogeneous color and then after that. So what was the different color?
The different color is just a way to represent that it has different scanners. Like the nodes have now a feature, and it's just different features, it's just it's just illustration to say the different colors represent different features for each node, which you then use to predict that.
So it's related to what I was thinking is how do you know that from the second last layer, the last layer, that the feature that you've extracted is related to the magnetic moment of the charge?
That is something you like in reality want to have it per atom. So in reality, we know that the node scalars are directly related to the atoms. So from directly taking the node scalars and then pass through in reality, just a linear neural network, we can in reality say then the linear layer will scale these node features to map directly into the magnetic moment.
So there's actually no activation function between the last layer.
There is an activation function as well.
There is an activation.
I don't remember which one. I will show you. There's activation.
There's also, so that means that it's not purely linear.
It's not purely linear. It's almost linear, but yeah.
Value or something.
But then have actually people started using this kind of PINN, the physical informed neural network, where actually the physics informed neural network, where the second layer. Let's assume a second layer. You assume it's a vector of magnetic momentum and also the charge, and then you just use some equations and to see would that actually be better.
Extract it out.
You can actually get a little bit more rich information from the second, because right now the second layer is still like a black box, right?
In reality, yes, it is a black box, the second layer.
Yeah.
I actually don't know if there's a new network like specific one. I think the reason why they did it to the second to last was the idea, they write it directly in the paper, it said they hoped that they could indirectly force some of the message passing to follow this atomic. But
it's actually forcing it actually
Yeah.
to learn the magnetic momentum. Yeah.
but it doesn't enhance the prediction a lot.
It's still black box, right?
It's not like
How do you force it? You don't regularize it.
no, they just hope they force it.
Yeah, so you're not
They
really
don't
forcing
have
it.
a
Yeah, so what I'm saying is if you can force it, actually like the second layer,
Yeah.
force it, there's some physical equation.
Correct.
That actually.
Yeah.
Then actually, then that's more, might be more.
It has to fit into some equation. You do some linear operations in that
one
layer.
could do that, and then in reality do a wait and say, listen, you need to follow this chemical rules.
Pei Chen is here, you can ask him. He's gonna be here already. I think he's already here. So you can ask him.
Oh yeah, he
I'll
should
see
know.
him next 2 weeks from now in Hefei, not in Singapore. I will ask him. He's a good question, I think.
I can see we're running a lot of out of time, but
There's no time for the group meeting. This is what you signed up for.
because
The group meeting is a very
I'm just going to
different.
mention some more questions. The issue is with these graphical neural network is you need data, and you need quite a lot. So another thing I've been working on is the active learning workflow. When in reality, we go in and train an initial machine learning potential, then we use this model to do a molecular dynamic simulation. Maybe it's not the best model, and maybe it will create some physical predictions. That's fine. I of course limit it, so if the forces on the atoms gets too crazy, then I stop and say, now I don't want anymore because I know the system has exploded. But in reality, we try to make a molecular dynamic simulation. Then from this molecular dynamic simulation created by machine learning potential, we do an active learning sampling. So in reality, we just ask the machine learning model directly, what structures are the ones you're most uncertain about? Why do you want to learn more? A bit like how Android do with the optimization algorithm. Like, where do you want to learn more? Then we take those structures, and it's a deterministic approach. So the first structure also the one, always the one which is the most informative. Then we take all these batch structures and do single point DFT on them. This single point DFT labeling can be used in two ways. One is you can validate your molecular dynamic simulation and see how well does it actually fit. The other way of doing it is in reality, if it's not good enough, you can see maybe the errors are very wrong. Then you take this data and add it to the machine learning force field and do the loop again. So do this step here, again, come back to D and do the validation and see is it good enough or not. So both use it to enhance our model and to validate it. And this is called the curator, and it is utilized using Perq, which is a workflow managing tools, which dynamically can train these models. In reality, I can submit this tomorrow, and then I will come back in a week or two, and then I have a machine learning model which has been trained this way. It's a very neat tool to use when you want to have data specific for a specific application.
So if you go back one step, I'm trying to think in terms of verb, right? I mean, I'm going ahead of the presentation.
Yeah. Then you can change the molecular dynamic simulation to be verb in reality.
Which is what we're trying to do in a way.
Yeah.
But what if we include the MD simulation? Because that's actually maybe a little more accurate in estimating about atomic positions.
Yeah.
So we don't need, I mean, you don't need to train the machine learning potential. You would use a machine learning potential, but use VERP and MD with active learning with single point. Would that be a loop?
One could do, yeah, one could easily do it. It doesn't matter what simulation you put here. I've used just elastic band, and that was just relaxation where I get that like kind of verb, and then molecular dynamic simulations. So I've done different ones. Like you could do that. The only issue is molecular dynamic simulation takes a bit of a time to collaborate. Of course, what I do in when I do not elastic band, where you get the energy barrier, is that when I have the barrier, I do a little molecular dynamics simulation step of some of the transition states to get out of equilibrium.
Nice.
So one could do that. Like maybe you will not be able to do an actual molecular dynamics simulation at the end, but you will have more idea of what is out of equilibrium.
Right.
So it could be an idea.
Martin, I'm a little bit lost here. Actually, like, what is the objective of active learning here?
The objective is to enhance the machine learning potential for what simulation you're interested in. So in reality, you can see here, I now have an example of these two materials. In iteration one, I did molecular dynamics simulation of these. In iteration one, you can see the machine learning energy is really scaled. Like it's not good. This like a machine learning model does not know what it's doing. But when I took these data, gave it back to the machine learning model, trained it again, did the same thing, and then I could see that it actually enhanced quite a lot.
So basically, it's basically like you tell, like initially it was not good, and then you pick your active learning objective, pick the points, actually then maximize the information.
Yes, exactly.
That actually helps the machine learning and make it so
exactly
to basically to do the self-correction.
Exactly, and we could use it to go from picosecond MD simulation to nanosecond in one iteration. That was quite good.
I think it's very, very good for MD to basically do something.
Yes, it's not only for MD. If you have outer distribution data you're interested in, then you can do that. For example, in now Keda's example is verb, where you, I will also come back to that, but where you in reality have different site disorder, different crystal sites, then you can do that, and then you actually go out of distribution and then train it to really model this simulation.
But that means you have to retrain your MRI.
You need to retrain it. It is to get it's to get system specific data. That's what it's used for. Yeah.
But then that means we cannot really use like a foundation model, which is like say like maze which had been pre-trained.
No.
Bigger, right?
No. In reality, I did not use maze for this because in reality you want something fast. Maze is not the fastest. One could use maze, but you in reality just want data in a clever way. So what I always recommend people is using this to gather data. When you have the data, train a maze model. Yeah.
Martin, like if you active learning workflow, it looks like you have to have like all the the DFT and the DSO.
Yeah, you need to, the active learning workflow is to get data.
That's part of it. I mean, like, we need to.
Yeah, you just want data. That's the whole idea of the active learning workflow. Get more data, system-specific data within a certain compound. In this case, I had these, like again, my force field, my material space here, and you can see I got around 300,000 DFT calculated structures from this active learning force field, where I have almost half is single transition line types, where I did molecular dynamic simulation on them as well, and the rest is multi-transition line, where I have multiple transition lines in the material. So this site disorder both happens in sodium when I remove sodium and when I add different transition lines. Because then we can use this data set to again train the machine learning module. That's the whole idea.
I feel we haven't used your capability enough. Like for example, the symmetry DOF stuff.
Yeah.
If you, I'm obviously drawing a connection from your diagram that you have in the previous slide. The underprediction of energy in this case comes from undersampling. What if that's really true for us too? It's like basically you want to sample from MP trajectory those conditions that have high symmetry DOF.
Yeah.
And then so now what you do with active learning workflow is similarly plot some plot. And then if you go towards, so maybe what is happening is that the symmetry is not inherently learned by the foundation models for the energy hull because they don't sample the high symmetry enough. That's the hypothesis, right? So if you just sample the low symmetry structures, maybe it's actually able to learn. So all you have to do is keep everything the same, but just you symmetry, which sample, because you already have a set of samples to choose from. You don't need to run MD. You just need to say, hey, I need to choose these MP trajectory compounds and then retrain. So you don't even need MD. It's a simulator. Right?
It doesn't matter what it is.
Yeah. Then you do the single point DFT and go back and retrain the model.
Yeah, it doesn't matter. One can easily do that. Then you do the active learning and ask what materials it actually
Yeah.
But the thing is, then because nobody tested on all the foundation models, so presumably they already seen all the others.
The thing is, and that's actually the thing, all the data on weight tested on now, he must say if I'm wrong, is that they were already in the training data.
Yeah,
that's why it was so crazy that it was so bad at the training data.
Yeah.
So even if you feel that thing, they already seen the data, like will that actually change the
But okay, think about it, right? The distribution of high symmetry degree of freedom points should be low, isn't it? Because
yeah.
I don't know if this is true because they're the low symmetry structures. So you in your distribution for materials project, even the trajectory. Actually, what we should do is sample MP. I don't know if Nongwei is listening. Not here. So just he's preparing the response to his paper anyway. He's not here.
Yeah,
Here. Hey, you should just try. Can you plot on any of the big data sets, MP trajectory or whatever, OMAT 24 or something? Plot the all structures inside this histogram with respect to symmetry degree of freedom. We know what it looks like for MP 20. Maybe just underrepresented. Then we need to artificially generate more, which is easy to generate with generative model.
You are assuming that our IP will be able to learn that.
Correct.
I mean, what if it doesn't agree?
Right, but let's say because trajectory data has millions of data points, you have 100 times more data in the low symmetry degree of freedom. So it's understanding that space really well, but it just has much fewer data. It just simply means that there's not enough data that it didn't pick up that. That's my hypothesis. I could be wrong, but it's computationally easy. And then all you need to do is use a generative model to only generate random structures that are low symmetry, which have high symmetry degree of freedom. They don't have to be meaningful, They just have to follow the Wyckoff side symmetries.
Yeah.
So our synthetic data that still follows principles of crystallography, that is just not realistic. And then maybe you pick up and model gets better. I don't know. It's a random thought.
It would be interesting. It would be interesting to see it get better. It will also be really interesting. Not getting better.
That's right.
Then actually experience that like sort of proof of noise theory.
Yes. That somehow there's something intrinsically wrong, which is not captured by yeah, exactly. Okay, sorry.
So now when we have this data, we can train the machine learning force field and stop. Now we have what we want. Now we can train it and actually utilize it. So I utilized it for out of distribution data, which valid different site resort materials, because I only did molecular dynamics simulation for site for nuts for only one kind of transition metal lines. I didn't do it for several, so I can test on that. And I also have a few structures where I do ionic relaxation, which is I also considered more than 2 types of transition metal lines. All these here out of distribution data points. So I think, Pablo, you asked about the ionic relaxation, and here you can actually see one in a little bit of action. So every point you can see where it moves a little bit. Does it still move? Yeah, that's one point of this is like where I use the machine learning potential. So it's like you use the optimization algorithm to change the now it's not moving to change the cell and the position of the atom. Very little, doesn't change a lot. It is, but it changes a little bit. Yeah, as you can see. So there's a lot of different, so there is a step, these ionic steps, and for each step, we use the machine learning interatomic potentials. This in reality, so what Keta said before, that my system-specific model, the C-plane model, can actually predict much better than the machine learning interatomic potentials. And that can be seen both in the energies, but also the forces. But one have to note the forces are actually really bad for machine learning potential. That's a general thing. Very good at predicting energy, but the forces it's really not good at. And one need really to enhance these things, and people are looking into how to enhance this.
What is the key challenge then?
The key challenge is actually from a machine learning perspective, it's the size. It's because you want to go from very high forces, large forces, to very small forces. So the forces I show here really varies. They do not vary a lot here, but in reality, you have a lot of different forces per atom. This is mean atom, but if you look at per atom, they actually vary a lot, the forces. And I believe, I don't know, but I think that is now looking at it, and I think that's the case. I think the size, which is the because the energies are very similar in size, but the forces can actually vary quite a lot. That's why when I train Xavier's data, I forcefully remove something where I say this is too high forces, because then the scaling would be too crazy.
It's just that, but is it related to the fact that it's just a derivative? Is it more sensitive because it's related to the derivative?
Yeah.
My impression was just that, right?
Yeah,
It's the first order.
That could also be a reason.
Okay.
I think from a training perspective, with loss function and so on, it's the scale. That's why you also really have high weights on the forces and the stress, because the scale are so small. Yeah. But atomic charges, we could see we could break them very accurately, one-to-one line. And we could see here that we could also play that's your question, they're directly correlated. So they could also predict it very well for the magnetic moment, even though charts that have some issues in some cases. I also did the outer distribution molecular dynamics. Maybe we just quickly because we talked a lot about this. So yeah, I did different transition lines, and now, which is very nice, is that I can model the atomic charge as a function of time. So in reality, when now it's in femtosecond regions, so we cannot really see any movement of the transition, the redox process of the transition lines. But for longer time scales, we can now model how the redox changes when the ion moves, which is quite nice. Yes.
It's a quick question, but like you said, you had like almost 300,000 PFP calculated.
Yeah.
Like I just to understand like the advantages. Like for example, what is so you have that in time frames, right? So
yeah,
what is your resolution of a frame? 1 femtosecond?
Yeah, 1 femtosecond. The thing is, this is directly what is called ab initio molecular dynamics. So this is like that DFT driven molecular dynamics I compare with the machine learning. So it's through a direct comparison I did this. Yeah. Yes.
Yeah, because like I mean, if it's only for 100 frames, then like why go to the pain to create these?
I can do several nanoseconds, but DFT cannot follow. Like DFT, if I want to do 2 nanoseconds ab initio molecular dynamics, it will take, and I kid you not, 200 years, because I have a frame of 1 femtosecond. Exactly, and 1 femtosecond takes, depending on the size of the cell, it takes between 3 hours to 10 hours.
Okay. So it's when you want to do faster.
Exactly.
Okay, good. Thank you.
Yeah, and now I think again I'm running out of time, so maybe I will skip some slides coming ahead. But now in reality, we want to go from this discrete potential energy landscape. I have here the different sodium levels, different charge states for the battery, and then we have the different transition metal ions on the y-axis. Once we go for this very discretized phase, we can get with DFT. So this huge phase we can get with machine learning potential. And to do that, we need to not search in blind, because I actually just did a test because somebody asked me the other day after our presentation, how many unique structures are there when I consider this dot here?
Yeah.
There is around 75,000 different structures possible at that.
75,000.
75,000. Not symmetrically equivalent that I'm running now, but I guess there will at least be half, which is symmetrically equivalent. But 75,000 possibilities in reality.
For each stoichiometry.
For each little dot. And in reality, this was when I only changed the sodium concentration. If I now also give it the degree of freedom of changing the position between iron and manganese, then suddenly it's, you can imagine it will be in million ranges for this little dot here. So in reality, we don't want to look at all possible combinations. We don't want to brute force. So that's why we want to look at global optimization algorithms. In reality, you go in and try to go to the lowest in energy using some of these algorithms. Now I've looked at four. The fourth one is future work, but I've looked at work, which is done by Andy. And then I've done cluster expansion, then I've done genetic algorithm, and then later on we try to do generative models for the purpose of finding the thermodynamically stable materials on reality lowest in energy at each dot. Because then we can get the convex hull and see where's the phase diagram. Like how does what's the profile of these materials look for each different transition metal line configuration. Oh, what happened here?
But the 75,000 structures probably are not, like, it comes back to my earlier question.
I think we talked too long, the PowerPoint. I will just quickly get up and run.
The difference in energies between them, is it very small or very large? That's at the end of the day, that's what comes out, right?
And that's the issue. It is unfortunately, as now way have shown, not very big. So I'm questioning these days, even with this specifically trained machine learning potential, if they're actually able to capture this. Because I think in reality it will be quite tough. Yeah, I need to find my it broke, so I need to find it again. Yeah, so that's why we try this global optimization algorithm to in reality find both thermodynamically stable configuration, but in reality also just get a broad idea of what's going on in each configuration. So we'll see. Stupid power thing. Come on. Why did it break? I think it talked too long.
Does not like you.
Yeah, I don't know why. It always shows this small little stuff. There we go. Yeah. So again, I think we're running out of time, so maybe I will skip one of these global optimization. Or maybe I'll just quickly show work so you can follow what I in reality want to do. In reality, we have a shift like this where you have partial occupancy of these elements. Then in reality, what we want to do is we want to make a supercell to really accurately capture how the different element when we position in this crystal is modeled. So we use a quite big supercell where Andy has set up a thumb rule, about 40 angstrom to really remove the periodic boundary condition buffering. And then in reality, we take these partial occupied sites and then occupy them by randomly, stochastically, with different elements, which is possible at these sites, still following the stoichiometry of this certain set file. And then we do a machine learning relaxation on them, so we can reality get the properties. We need to do this for a lot of different possible combination of putting these atoms at different symmetry sites to get the property distribution in reality. We cannot only have one particular cell. We have a lot of different cells with different compositions, because then we can get this property distribution, which can look like this, where you have here a 2-2-2 supercell, and a 3-3-3 supercell. And you can see here when we enhance the supercell, you get a much better Boltzmann distribution, in this case for the density, and it does not change a lot if we use 400 different samples of these or 1,000. That's the reason why Andy chose in his code to only do 400 in reality. So in reality, this code is very good to get an overview of how the properties of this material looks like. But when you try to do it for this sodium ion phosphate, as I was doing, it does not capture the experimental phase. So I do not find the lowest in energy configuration.
So can you tell me what you did here is each dot
Each dot,
you did work on.
yes.
And so you have 400 structures there are 400 structures for each vertical line.
In reality, no.
Okay.
That I could have done.
Okay.
Then maybe I would have captured it. This is just in general 1,000. So it's just
So-
random.
But that's what you need, right? For each stoichiometry, you need 400.
Yeah, in reality, but I can do that, and that will be fine. But I will still question if we are able to capture this low energy, because if I add it directly,
Yeah, you're probably oversampling. So the question
in
is
reality,
different.
we maybe oversample, but we also maybe will not capture this particular dot we are interested in. Yeah.
Because the problem is not often this.
It's not, it's random search.
It's a random search, exactly. The verb is a random search. One could add, maybe we'll do this in the future, global optimization directly into it. But
No, but I think the question you're asking is a bit different, right?
Yeah.
In verb, what we're saying is for any vertical line,
Yeah,
how many points do we need in order to estimate the average property
exactly,
value?
exactly.
Given that if you look at the relative energy, it's small.
Yeah.
It's 100 MeV, which is like at room temperature.
Exactly.
Okay, a little bit more than room temperature. I expect it to be lower, right? But now the question is different, which is saying we actually don't need to sample completely. We need to get the convex hull of the stoichiometry.
Yeah.
So then in this case, optimization makes sense. I agree.
So yeah, if you want a specific low energy one, then global optimization is smart. But if you just want an overview of the property,
I agree.
then verb is smart, because then we don't bias towards low energy, we bias towards the whole phase, which is positive.
I missed that yesterday. Now it's clear.
Yeah. So that's but in reality, again, I'm interested in these phase. I'm interested in the voltage profile. I don't care about all these in reality. Boom, I want them gone. So that's why I use the global optimization. But running out of time, maybe I will skip cluster expansion and then go directly to genetic algorithm. Because I think there will be quite some questions when I begin introducing this. But I will just, instead of see cluster expansion as a model, which in reality can predict the energy of in reality is a model which can predict the energy of different crystal structures linearly. So in one microsecond, I know the energy of this particular structure. So cluster expansion is really fast. But to really use cluster expansion, you need, again, some training data. So I trained a cluster expansion model on DFT. And that DFT data set, I use machine learning potential to get the same. So then I've trained the cluster expansion on DFT and machine learning data set. And then I did a Monte Carlo simulation where we start we take a big cell. This is not that big, it's this cell here, right? And then we start from a very, very large temperature, and then we do annealing until we reach the temperature we're interested in this case, 2K. One could also do 300K or something like this, but you use Monte Carlo to really go slowly down. So in reality, the entropy will slowly go towards the energy, the structure of interest. So the T Monte Carlo simulation found this to be the lowest in energy. The machine learning Monte Carlo found this to be the lowest in energy, but experimentalists found this to be the lowest in energy. They have found that this is the structure we are interested in for sodium 0.66 iron phosphate. So I asked the cluster expansion model, what do you think? In reality, the DFT cluster expansion model finds that its own phase is the lowest in energy. This is millieV per formula unit. But when I do the DFT calculation, these three systems, I see, that's a spoiler. I see that the experimental phase is indeed the one which is the lowest in energy. I did the same with the machine learning cluster expansion model. Again, it finds its own to be the lowest in energy. But again, the machine learning potential, when I do the calculation, it finds the experimental to be the lowest in energy.
The means is the cluster expansion not really fine. It's not
Exactly. That is exactly the point. Then I said, okay, you know what? Let's do it. Let's see if the cluster expansion, if I give it the data which it's looking for, if I gave these three structures to the cluster expansion and trained it again, can they actually capture the experimental phase? For the DFT cluster expansion, it could Not clearly, you can see there's only 6 MeV per formula unit difference, but it could find the machine learning cluster expansion, the same setting, could not. And my hypothesis for this is that machine learning have an error, of course, we cannot predict perfect, and the cluster expansion have an error, it cannot predict perfect. So because of the accumulation of error, it might be difficult to actually capture this experimental phase accurately. And for this reason, I looked for other optimization algorithm where I don't inherently train a model, but use the machine learning potentials directly. That's what I use genetic algorithm for in reality. Again, I will not go through the details because Shuya also wants to talk at some point. But genetic algorithm is a global optimization algorithm, which can, through generations, slowly converge towards the lowest energy for different concentrations of sodium. And I did, you can see that 20, 100, and 200 generations. For each generation, there was 100 structures. In the end, I did 20,000 structures.
So you're doing
What's the difference?
just longer time.
No, yeah, it's basically how much data I probe. So you can see here I only probe 2,000.
Okay.
Here I have 10,000. Here I have 20,000. But in reality, you can see here the energy does not really change. So in reality, there is a little gap here, but it does not really. You can see this like it's not a big change between these two. So one could argue, and we actually can stop it after 100. But it's a stochastic algorithm, so I had to do it 6 times. And one thinks 200,000 is a lot. Each, like doing this here took a day. So maybe it's worth it.
Just the machine learning potential.
Just machine learning potential, no DFT. The issue is that I actually get not the 2/3, but I get something very interesting here at the 0.1/3. And they question me, okay, why the hell does it not get what I want? Then I, in reality, looked. You can see it is low in energy. This is the one I look for. Then I took these structures, 10 of these. You can see here, together with the experimental phase, and they are very close. They are just not the experimental. This is 10 structures I probe, and they are close. Like they get the idea that they should, like the sodium should be different in each layer here, but it doesn't get this accurately. And now comes why I'm beginning questioning things here, because then I did the machine learning optimization of these 10 structures. I did them against the DFT, and the black one here is the lowest in energy, the red one is the second lowest in energy, and the third one is the third lowest in energy. The blue one here, yeah. So the experimental is still the DFT, clearly the DFT is lowest in energy. The DFT knows that this is what the experiments find. And that is not the same to be said about the machine learning potentials. My model, CK, like does not know if this is the lowest in energy or this is the lowest in energy. It confuses itself. Not a lot, but it doesn't exactly know. The worst is actually made by I trained it with my data set. It has the tendency to really get the energy the same for a group of material that does not look the same. And this is a bit of an issue. Chancellor is actually the one performing the best, which is a bit annoying, but that's how it is. But yeah, that actually captured it correctly. It has difficulties finding the second lowest in energy, but yeah, that's how it is.
But you don't know how generalizable this is. This is just for one compound.
Yeah, this is one compound. This is the simplest compound. That's the issue. So if we want to have different transition lines, this is only one kind of vacancy, like one kind of disorder. We want 2 different kinds of disorders simultaneously. So this is a bit of an issue. And Mays label these here as the same in energy. And, yeah, that's not good.
In terms of similarity, are those the structures that are most similar to each other as well?
How will you model similarity?
And for my case, I use so, but I don't think it's possible here. I don't know how you do it.
You cannot really say which is similar or not. I think it's difficult directly. I can probe, I can move these atoms a little bit away from equilibrium, and then that will be the one which is the closest that I could do and test. But yeah, I think it's a bit the same as this. No, which one was that? One which is very close. The second to last, this one. This was the second lowest in energy here. I took these 4 atoms and moved them, one down in the vacancy. Yeah.
But I think the approach is promising, even though you don't find the lowest energy because
No.
look at-
Something is promising.
yeah, because if you look at the difference in the energies of the hull,
Yeah.
it's like not even 0.1 EV, not even 0.01 EV.
No.
And it makes no difference. We should just put a window and say, hey, there are all these possible structures.
Yeah.
And anyway, this is very different in composition space from this.
Yeah.
So 66% is very different from 33%.
Yeah.
In the experiment, we can control it.
Yeah.
So if I look at the local phase space, you actually found the lowest.
That's also what I feel. Yeah, I agree.
You're not far from.
One did not agree, but I agree.
Okay, good.
So now
As an experimentalist, I'm happy. Okay, this is okay. We can go there, and then you know that energy structures should be feasible,
yeah,
right? I'm more worried about the fact that these are all very similar.
Yeah.
How do I know that this is what you get?
Yeah.
I
That,
think
that is-
probably that these two are also.
that is also a concern.
That's more of a concern than the globe. See, it really depends on what you're asking.
Oh, I've stopped sharing the screen. I think my connection broke. I think my internet is bad, but in reality, I'm also done. I don't know if there's any questions online. Let's see. Now everything
Where's
will.
the screen?
Now the screen is also gone. Let's see, does it come up?
It'll come. Go back to it. Oh,
It's
there.
coming now. Yeah, so I don't know.
No, you're not sharing it.
I'm done.
Wait.
I
But are you not sharing on
don't
Zoom?
know. My internet broke.
Your internet's broken.
That's how it is. It's also curious time, I think now.
You don't have any culture slides?
I do.
Okay, how about just reconnect your internet? We'll come back to culture slides. You cannot end without culture slides. It's
I
rude.
have a very beautiful picture. It's because I looked out of bedroom.
Okay, we do culture slides. It's okay. Our guys are used to being late and into stress. Usually it goes till 3.
Then while I'm connecting, I can just
Yeah, I don't think this is too bad. Huh?
I don't think so too. Then
Is it something that you have to run? Like, for example, here there's no MD, right? This
No
is
MD.
just pane, C-pane?
and Mason Chartered. This is
Oh, I
CPA,
made it.
but I also did it for Mason Chartered. And we actually they get Mace. Looking at Mace, it is the one which is the worst. Looking at that plot, unfortunately.
So what do you have to do here for the generative? You just need to start with some partial occupancy
Yeah.
and then just need to run it through the potentials.
Yes.
Basically, you could do work to populate,
In reality, yes.
or you don't need work. You use GA to populate structures, then use and calculate the energy. It's really fast, right?
Yeah.
So can we run it on the 7 structures that Andy has put in work?
Yeah.
Let's do
Yeah,
that.
we need to do it cleverly, but yes, in reality, yes. Okay.
Andy, do you have the bandwidth to do that? Because you need to do Jayanta samples first. But this is not computationally expensive. If you can chat with Martin to see, it'll be a good learning one for us. If you can run his, or just give him
Maybe
some
I'll also
structures.
talk with Shanghai that maybe
Maybe Shanghai.
the method I'm using might not be the most efficient one.
Okay. Yeah.
I can't do that.
But this might be the right, I agree. This might be the right way to think about phase stability.
Yeah.
Not through just this gen.
No, that's actually the other one before the prototype, and then we're running late. Run. Back. Bum. All the way down. Maybe I say something similar. So in reality, yeah, that was actually a quick slide I had here because I didn't
On the
want to-
generative model.
Not that one, this one.
Mm,
Which is in reality, what we could do is we could use the global optimization here.
yeah.
So in reality, you can use this gen to find the compound you're interested in, but then you can do the global optimization with either verb or some of the other things. So
Yeah.
that's maybe the right way of doing it. Maybe we need to discuss it in.
Although the other one might be computationally a little more intensive, this might be more efficient, but that's tractable right now.
Yeah.
This might require some funky finding. I don't know, actually.
No,
I think
no.
this is what we need to figure out.
Oh, yeah. So
I think
those,
in terms of novelty, this is cooler.
yeah, but I think this is better. Yeah, so those who does not know it, I think Raymond already presented this. So I think maybe people have seen it before. But yeah, the goal is now I have done do it, and we found that this is not that clever. In reality, it's brute forcing still, even though I have the global optimization algorithm. So maybe one should instead go and use this generative model to find possible compounds, do global optimization, maybe together with active learning, then go in and do comparative experiments.
Yeah. But what does your generative model really give you?
The generative, what the hope is together with the Nano Shuya is working on it, that together we could somehow, in this big phase space I have, I will not go all the way back there, I can in reality go and look, like then it will help me find, instead of looking at all lines, then in
which lines?
Say, what lines should you consider more in depth in this Vortex profile,
But how did that happen in this gen? So if you go back in the paper that we've sent out, how come you only have this? So what was it that made you choose only these songs?
This is based on what ICSD have in that database. It's ICSD based. So instead of doing only ICSD based, we do ICSD based.
So these compositions are already in ICSD?
Yes. No, they're not. They are extra. They are taking compounds which is already disordered in ICSD with these elements and saying, maybe we should try this with this compound instead. That's basically it.
Okay. I don't have full confidence in that.
No, I don't. That's why we need
sampling is better.
That's why we need to have something like multi conditions. But I'm looking through it. Yeah. A bit quick wrap up here in the end, but I think that's fine. In reality, this is what I'm considering, and I'm not done. Need this whole thing here, and we still have not fixed the one above. But maybe we will do that, and then of course thanks to the collaborators and so on. For culture science. Huh? Of course. For culture slide, I went to Boston with Andre and the others, and we did do it was a nice conference. We did do curling. You can see it like it's so cold that we have to warm us at fake fire, and we also tried the local delicacy. It was crazy expensive, but tastes quite good.
Delicacy is overrated.
Yeah.
American food is not really delicacy.
And then I also went to EMIS in Strasbourg, where I presented a similar work as this. And Strasbourg was a nice city, not as cold, and that was a good trip. And then, as Peter know, I was gone the whole April because I went to Nepal with my father because he had a midlife crisis in the 60s. I don't know why, but he wanted to climb the Himalaya mountains, so I went with him to go climbing, and we tried everything. We went through snowstorms.
Wow.
We got beer with a beautiful view and also sun sometimes. And unfortunately, he gave up at the last day, so he had to take the public transport of Nepal to go to one of the mountains. But yeah, it was a good trip. We saw culture and did some hiking, and so that was I would recommend to go to Nepal and go into the Himalaya mountains. Yeah, especially this Annapurna range. It is it was a good experience.
How high up was it?
The highest I went up was 4,000. 4,000, yeah.
Did you get altitude sickness?
I actually got altitude sickness here, which is only in 3,200, as you can see here. But that was because I ran. So that was maybe not clever to run 800 meters up. That was maybe not that clever. No. It was because the plan was to go here during the night actually, and then come here and see the sunrise. But there was thunderstorm in the night, so we could not go. But the thunderstorm cleared in the morning, and then they said, "Oh, doing the plan, we cannot really go." And then I said, "What if I run?" And then I ran.
Oh.
Yeah. So I got a bit of altitude sickness here.
Nice. Very cool.
Cool. Then I will hand it over to Shuya.
Nice one. Lots to do. The fun has just begun. Shreya, you want to come here maybe? Quick coffee break. Like 2:30 we start. I'm going to get some Milo.
So it just needs like one transfer or two transfers to get there.
Okay, guys, online, let's start.
Okay, so hello everyone. I'm Shuya, first year PhD student, and today I'm going to talk about this provocative title. All AI models might be the same. Okay. So let's
Please say all AI models for material science.
no, this is sort of the lesson from language modeling and vision models, and I will talk about like implications from variables. So let's start off with this game, like Mussolini of bread. Like there are basically two players to this, and I imagine something, and you guess what I have in my mind just by asking like whether it's closer to Mussolini or bread. So like, is it closer to Mussolini or bread? So Mussolini. Is it closer to Mussolini or Michael Jordan? I guess Mussolini. So okay, they're thinking of a person, but not an athlete. So is it closer to Mussolini or Bill Clinton? So Bill Clinton. So it's more like a modern figure than a dictator. And then is it closer to Bill Clinton or Grace Hopper? And Grace Hopper, we've been into science and tech. Is it closer to Grace Hopper or Albert Einstein? Albert Einstein. Then is it closer to Albert Einstein or Richard Feynman? Oh, you got it? I was thinking of Richard Feynman.
Like 20 questions.
Yeah, sort of the 20 questions. So why does this game work? One explanation to this it could be that like we all have like shared sense of semantics or kernel to like relate things to each other and measure the similarity between the different concepts. And this is based on the critical assumption that like there is only one way in which things are related to each other. And this comes from the underlying world we live in.
It's called Bayesian.
Yeah?
That's my hypothesis. Okay.
Yeah, so then here's this like last year, the ICML position paper, there was this paper called Platonic Representation Hypothesis, where they basically say that the neural networks trained with different objectives on different data and modalities are converging to a shared statistical model of reality in their representation spaces. So what it means that we have the same underlying reality, but there is a different way to sense the same reality, either through be it vision or text. And then we have each neural networks to compress these modalities into each representation. But at the end of the day, they're converging to a shared representation. And this is not some like crazy philosophical hypothesis, but there are quite a few empirical observations to show this.
But okay, go back to the previous slide. So let's say you represent the image space by some Latin space,
Yes.
and you describe this in the text space in some Latin space.
Yes.
How would you show the similarity into Latin space?
Okay, so the way they measure the similarity is by the kernel. The kernel is like measuring the similarity between the different data points.
Okay.
And the vision models and language models has their own kernel. And we measure the similarity of the kernel.
You measure the similarity of the kernel.
So like we have apple and orange.
Mm.
The vision models measure the similarity through their kernel. Like they basically measure the distance between different two data points using their kernel. And language models also have their own kernel. Yeah, sort of embeddings, but they call it like as a like kernel.
In a Gaussian process, the kernel is a set of basis vectors, right?
Mm-hmm.
In large language models, what is the kernel typically?
I think it's sort of the embeddings or the hidden states within the model. And it also depends on which layer you extract those embeddings from, but
Interesting.
Yeah.
Okay. I
Yeah.
can't picture that. Okay, I think about it.
but
Okay.
they define the similarity as in the similarity of the kernel for each models. And one example is this, like there are data sets like pair of text and image, and the vision models are solely trained on the image, and the language model trained on the text.
Okay.
And then what they say is that as the size of the data sets getting larger and larger, and as the performance of the language models is getting better, the alignment of the language model to the vision models are getting stronger and stronger. If you, as you see the diagonal trend, the trend in the diagonal.
The trend in the diagonal basically is that the correlation is strong.
Correlation is getting stronger as
Yes.
the performance of the language model is becoming
Correlation
better.
Stronger.
That means
Correlation is just a line between the two, right? As long as the slope is 1, the correlation is strong. So
So the correlation is the y-axis.
yeah, the y-axis,
Oh, okay, I see.
alignment to vision,
Sorry, I
language
thought
to vision,
some metric, vision, metric for language.
Oh, no,
That's
no.
not what it is.
alignment in the vertical, and the
Yeah.
language, the performance of the language model in the x-axis.
I see.
And as the model is getting bigger and bigger, it's
Mhm.
aligning more towards the vision models, even though each model are trained on
But
like
what is considered a high value, like 0.1 to 0.18 is like, I mean, it is true, but like, it's still like a last distance to one, right?
yeah.
But it's nice to
I
see
mean-
trend.
At least with some like trend.
So is the perfect alignment 1? The current alignment to whatever D move to Dino V2. Is
I-
perfect alignment 1 or is it something arbitrary?
That I'm not sure. I need to check.
Dynamic is the vision model
Hmm.
that you.
Yeah, so it's a kernel alignment, as I'm assuming, between the kernels for large language model and the kernel for Dino
Yeah,
V2.
that is correct.
And some measure of alignment of the two, some metric of similarity between
Yes.
the kernels. 0.17 is obviously better than 0.1, but I don't know the upper limit is 1.
It is all abstract, all this as a scatter. I think it's looking at its embedding, because there was a previous paper, I think the year before, so they talked about this, they said that if you train 2 different LLM models, they, with same data set, same training, they actually end up as a very similar structured latent space.
Yeah. So it's embedding.
The idea here is that small that was
Mm.
in the line, right, is how close are the latent spaces, right?
Yeah.
In
But-
terms of structure and like the alignment of all the different training objects.
That's correct.
So for a 1K, it's actually says that as you're getting higher in training, you are getting closer and closer to what the Dino V2 models would have been, without actually being a Dino model.
That's correct. Yeah.
I mean, to put it in a lay term, as much as I understand this, like, say I have a carrot and a dog, and the spacing between a carrot word and the dog the word would be similar to what my spacing between carrot the image and dog the image is in Dino V2 in an ideal case scenario.
Yeah, exactly. Like they measure the closeness between this apple and orange in a similar way.
Yeah, but I think the deeper idea here is that the embedded space should be well learned, the more number of parameters you have.
Yeah.
That's the idea, right?
Isn't the whole learning lesson is that it's arbitrary, right? Like you learning it as an image or learning it as a text, they should be fundamentally the same.
Hmm.
That's why the correlation is getting higher.
Hmm.
Yeah. Contextually, it's the same thing, right?
Yeah.
Be the image of input.
I mean, that's the hypothesis. As long as we learn about the shared reality, either through like whatever the modality or whatever the model architectures. And they argue that these are attributed to 3 selective pressure in the representation space. Like what's the driving force in the representational convergence? And one such pressure is the task generality, where they basically say that as the model trained with like increasing number of tasks, they're subject to pressure to learn a representation that can solve multiple tasks at the same time. So each task brings their each gradient in the hypothesis space, and we'll get like the fewer intersection that can solve multiple tasks at the same time.
This is the problem for Andre's second PhD.
I'm
One piece
gonna
of-
talk about this.
Oh,
Okay, that's nice. So this is one selective pressure that is driving the convergence. And the next is the model capacity, where they basically, the left diagram shows that there are 2 small models, but they might not cover the optimum. And they find there like different solutions to that. But as the size of the model is getting bigger and the models become more capable, they cover the optimum. So they converge to the same optimum representation. And the last is the simplicity bias, where they basically say as the so there are multiple like larger coverage of all possible ways to the same data, but models try to find the simplest solution to solve the different tasks at the same time. Yeah, so they argue that there are such like three selective bias that is driving the convergence in the representation. So the Platonic representation hypothesis seems to be true in like vision and language. What about molecules and crystals? Like, do we see any interesting examples? And the first thing came to my mind is this, like this year, this is from the Rafael Gomez group in MIT, and this is presented in this year's ISML. And the task is this, they have two different models. One is MLIP, the other is the general models. And they saw the similarity in the false prediction and the conformal generation task. They're totally two different tasks, but they have the same shared reality that is both about molecular geometry and energy. And MLIP is based on the message passing neural network, and generative model is based on transformer. But there are some like mathematical equivalence between the score and the force. Like, so they argue that we see the representational convergence in the MLIP trained to predict the force and energy, and also the generative models for the conformal generation. So they took this idea of the representational convergence, and then
The metric for convergence is well known.
yeah, they also use a similar metric. This is called central corner alignment, that kind of stuff. And they introduce these like representation alignment loss in addition to the diffusion loss. And they basically nudge the hidden states in the diffusion models towards the representation in the MLIP. So even without this representation alignment loss, we already see that hidden states in the diffusion models aligning towards that in the MLIP. So by explicitly introducing this representation alignment loss, we drive it towards the convergence. And as a result, we see the faster convergence and the better result.
What
in the
is
general
this similarity in Z of n and H of p? What is that?
Sorry, which?
What is inside the similarity metric there?
So the Z is the
Latin space of n dimensions.
yeah, the representation in the MLIP.
Okay.
And then H is the hidden states in the diffusion models. And this H function is the one that maps the hidden states into the representation in the MLIP. And they encourage those like convergence by explicitly introducing this loss function.
What is capital N?
This N, capital N.
Total number of,
Yeah.
Total number of samples.
on the batch to batch basis, right, on the loss function.
But it should just be.
So you're still getting the mean similarity for all samples in that batch. As you are running by default by default.
Nice. Okay.
Okay, so what's the implications for us? Like, what can we draw from this in the crystal modeling? And the first thing is, like, as Norway introduced last week, like the issue with MLIP that underpredicts the energy, and that is related to symmetry degree of freedom. So there is this model called DeepCSV++ that generate structures under the constraints of symmetry. So they learn the score with symmetry constraints. So if we nudge the representation in the MLIP towards that in the DeepCSV++ by explicitly introducing this like symmetry alignment loss, the kind of stuff, then we might be able to, like, this could be the one solution to, yeah, to solve the underprediction related to the
So
symmetry.
I think what you're saying is that what we've done so far is trying to regularize with respect to symmetry of freedom. But perhaps a better way to look at it is if this CSP is a model that captures symmetry well,
Yes.
the way to really use that information is not regularization, but looking at Latin space similar
Yeah.
and using that as a loss.
That's my hypothesis. Yeah.
Yeah.
And the second point would be that, like, we have bunch of different crystal channel models right now, but they perform like more or less the same in terms of the benchmark we
This
already
was
have.
my first part of the second slide that you sent.
Yeah.
You just compare, take all of them, the generative models, and just see what's
Yeah,
the representation.
yeah, so my question, yeah. Are there
Mm-hmm.
like, are we converging towards something or not? Like, if yes, then we should seek it, like the kind of.
Yeah, we should do it.
Yeah.
We should be the first ones to do this. Yeah.
Then if you're not converging, then what's the like misimpression? Is it the architecture or the size or like
Yeah.
task or modality? Yeah, that's my question. And the third point is like there
Yeah.
are property predictions, either composition based or structure based, but we are getting like more or less similar result.
Yeah.
Like could this be because of the convergence in the representation space?
It's a great master's problem.
Yeah.
Because just if the logic to know the MLIP representation is well known, then you do it for all. First of all, you compare all foundation models.
Mhm.
You take ESEN and you do it the same, and then look at are they all learning the same representation from the same data? Then you do the same for generative models, and then you could compare composition structure, and you have a metric to say the learned representation are not the same.
Mm.
And I did not know people had done this. It was pretty cool.
But
Yeah. Sorry,
You want to say something?
yeah, but it's more here. Is this a hypothesis that the composition only models perform better than the structure based?
It's property
No, no.
dependent, is what the hypothesis is. But certain properties do not rely on structure, supposedly. So composition is sufficient. So if you even show that it's true for certain properties, but not for others, that's valuable.
But is this true in reality? Because it depends on the property, right? If you're interested
Yeah, it
in-
depends.
Yeah.
Definitely depends.
So if it's a general property, I agree, something like thermal conductivity or,
Yeah,
energy
structure is important.
exactly, or anything above the whole, or yeah.
Mhm.
Structure actually predict instead of input.
No, I think you both of them have inputs, but you represent in Latin space and then compare that. That's the idea, embedded space.
Oh yeah, so the other thing that this just now kind of made me remember was that like in molecular representations you can do how do you encode them for machine learning algorithms? You have the selfies, you have like smiles, blah
Yeah.
blah. And I remember in the paper from selfie, something that I always thought that was quite interesting that they were arguing for was that I can't remember what metric they used, but they showed that using that representation was better or more efficient
Yeah.
to train the models. And I don't remember if it was less epochs or I can't remember.
Yeah.
But like something like that, if you find if they are converging to a representation, can you also kind of back engineer what is the ideal way to also input this information?
Mhm.
I think in general, I know that people are thinking about this embedded space for proteins and stuff too. Same question, right? What is the minimum model criteria that is required for data? So that for molecules, proteins, crystals, it's all the same.
Yeah.
It's just that we're more familiar with these models, so you might as well use these. So nobody's done this for inorganic materials yet.
Nobody has done that.
The data size of inorganic materials is quite small compared with what the first graph.
That's true. It definitely depends on the scale.
So you might be at a
That's-
0.1 on that first, less than 0.1, like the number of parameters we have.
Mhm.
But I remember the ESEN model is 200 million data points. And number of parameters like 200 million, something like that, right? That order. It's like or 1 or 2 orders of magnitude smaller than the data size and number of parameters.
Mm.
Very cool.
That's all.
All right. Can you send this slide to me?
Sure, sure.
Dwayne is very weird at putting together a proposal and Kind of nice that you're thinking of us.
Okay.
He has an army of master students.
Who?
Dwayne is a professor in NUS, and he's directing the AI science master's program in NUS. And so, by the way, if anybody wants to volunteer to teach, he's looking for people to teach AI. Okay.
I'm looking for learning.
Learning. You can join my course. But somebody will teach it. So Danny and Ivan are going to teach this Friday. If you guys want to join, that's totally up to you. Friday, we're going to do open trons, simple homework. Danny and Ivan have. And then the following week, we'll do generative models. If you guys want to learn, come to class. I will send you the information. So you can learn it.
And indeed,
Sure.
Yeah.
Yeah.
Everything there. Please.
Yes, teaching 5 and a half.
You want to do it next week?
That was.
No, next week I have some action.
Gonna be half an hour or 10 minutes?
Or simple.
And maybe 12 minutes.
12 minutes. Are you sure?
that's very precise.
Precise. This is leftover from the previous meeting
Ah.
because it went too long. So you're not the only one that goes too long.
That's what they have.
Nongway is our legend. You turn on your audio.
Okay.
Good. I like this. Video on, audio on. That's the way to do it. Okay, symmetry properties in some.
Okay, let's start. My name is Jiang Hai. Good afternoon, and I'm a first year PhD student. And today, I will talk about symmetry property and synthesizability, and maybe the correlation between this. Okay, so let's start with two principles or laws. The first one is the Newman's principle. It states that the symmetry operation of physical properties actually follows the symmetry operation of the point group of the crystals. So actually, it attributes the response of physical properties to the atoms that make up these materials. And for the Curie's laws, it extends this principle into the physical phenomena. And he says the asymmetry creates the phenomena, so that any physical phenomena comes from asymmetry.
The phenomena is different from property.
Yeah.
What is the difference between phenomena and property?
So physical property is intrinsic property of a materials, but a phenomena is like it's a process.
Process.
Yeah. Process.
Symmetry operation.
For example, let me take a simple example. For example, the stress or force. The force of a force or stress of a crystal or lattice actually corresponding to the atom stress in the microscopic scales.
So like kind of thinking like
Mm.
for like a tensor, the property is expressed in tensor.
Yes.
So I was thinking simply would be, in my mind, I was picturing if you have an anisotropy
Yeah.
in a C-axis crystal, like a van der Waals, it must be reflected in a symmetry operation to this point group of the crystal. Seems reasonable. Right?
Yeah.
That's what I was thinking. Yeah.
Yeah. So I'm considering
about symmetries in physics. So what's the difference between symmetry in physics and symmetry in material science? So I think because of the two principles or laws as the previous slides, people are considering more and more on symmetries in crystal generations, like space group symmetry, or basically the equivariance and invariance in model architecture, right? So in physics, actually, the symmetry means the physical or mathematical features of the system that is preserved or remain unchanged under some transformations. So here comes the unchanged, so that symmetry actually is another way to say invariance. So when we talk about symmetry, actually we are talking about invariance. So there are like two categories of symmetries. One is continuous symmetry, and we use Lie groups to describe it. And the other one is discrete symmetry. We have finite groups. For example, the space group symmetry is a typical discrete symmetry, and we use space group to describe it. So here I compare the invariance in machine learning models and physics. So actually, I think this terminology has some difference in the definition. Like the invariance that defined in machine learning actually is on the spatial transformations. Is that true? So like when we say this model is invariant, for example, translation invariant, that is when we translate the, like, for example, image, the result can be the same. And the equivariance is also like the transformation is corresponds to the transformation of the input, the output transformation, right? But in physics, it's a little bit different, because in physics, we are not only consider about spatial transformation, but also the time transformation. So I think the invariance in physics is equal to that in machine learning models, but the equivariance actually it's a high level form of symmetry. So it shows the invariance of the rules or relations between objects. Recall that the input transformation corresponding to the output transforms corresponding to the input. So actually the truly invariance quantity is actually the rules, or we say the relations between the input and output. So here comes the next theorem. We call it Noether's theorem. And she said any differentiable, or we say the continuous symmetry. Any continuous symmetry corresponds to a conserved quantities. So in physics, we have a lot of conservation laws, right? For example, the energy conservation actually refers to time translation invariance or time translation symmetry. And we have linear momentum conservation and angular moment conservation, and also the electric charge conservation. So all of these conservations have the corresponding symmetry in physics. I think it's the origin of this conserved quantities. So why invariance? Here we think about symmetry breakings, because
Go back one slide.
okay, go back.
This is the continuous symmetry.
And yes,
All of them here, right? Charge, momentum, energy.
yeah,
Unless it's quantum. Right, in which case it's quantized.
quantized.
So if you think about space group symmetry,
Space group
what is the
symmetry.
conserved quantity there?
I think I will mention it after.
Okay.
In depth. So let's see. So let's talk about the symmetry breaking. So basically in physics, the symmetry breaking actually refers to a disordered but symmetric state to an ordered but less symmetric state. Actually, this quite like counterintuitive, because for example, here I show these two pictures. The first one the ball stand on the top of a hill. We said the position is symmetric, right? But it's unstable. It will finally fall into two bottoms of the hill, right? But it's but either the left one or right one. But no matter no matter where he fall into, the result is unsymmetric.
Yeah, but why is that ordered?
That's what I want to say in the next slides.
Okay.
So in physics, the order and disorder, I think it's quite contradictory concepts with the concept that we usually use in like crystal structures. Because we say we have ordered structures and disordered structure. So in physics, order means the long range correlation or spontaneous symmetry breaking in the system. But for disordered, we say it has short range correlation and it has more symmetrical on the microscopic scales. So in this figure, you can see first one, it's disordered because it's more symmetric. And the second one, it is ordered. We'll see. So the picture on the right top is a typical disordered structures, right? But in physics, we say it is ordered. So why is that? Because look at this picture. So for every site, we have a mix of two elements, right? So if we treat it as a whole, it has a specific symmetry. Is that true? But if we want to truly synthesize these structures, or if we want to do some depth calculations of this structure, we should like make a supercell, because every site actually it can only occupy one specific items. The occupancy must be one. So in this case, the supercell we made is like disordered structures in material science, right? But in this illustration, it is ordered if we treat the mix of two atoms as a whole. So this is order and disorder, the meaning of the difference meaning in physics and material science, I think. So in physics, it more focus on the rules and relations, but in material science, we only focus on the spatial quantities, spatial change. That's it. So how many orderings are there? We have structural orderings, we have compositional orderings, that is like site disorder structures. And also we have charge ordering and magnetic orderings. So for this picture, we can see that the systems forms a certain consistent pattern on a large scale. So we say it's ordered in physics. But if you want to turn it into a real world to calculate or synthesis, it must be disordered.
I think you're talking about ordering of site where you're giving an extra degree of freedom. You're saying that site, I don't care what's in there, then it's ordered.
Yes.
So you're reducing complexity.
Yeah.
Because you're caring about symmetry or something.
Yes, yes.
But in material, what you call material science, you're saying that the location of the atom is important. In that case, you cannot randomly assign an atom to it.
Yeah.
That's
So
the point, right? It's a fundamental
we are talking about the pattern and the object.
Sure.
Okay. And so typically there are two different kinds of symmetry breakings. First one is simultaneous symmetry breaking, and next one is the explicit symmetry breaking. So for simultaneous symmetry breaking, the equation of the motion, or we say the systems, keeps invariant, but the ground state or vacuum state can be variant. So in physics, the vacuum states refer to the lowest energy state. So it's like the ground, we say ground state is equal to vacuum state. But for the explicit symmetry breaking, the equation of motion, or we say the system itself, actually can be variant. So this is a different of two types of symmetry breakings, and we will look into it one by one. So first one is the simultaneous symmetry breaking. Is the picture illustrated here is actually an example of simultaneous symmetry breaking. So here is some Biot potential, or we see the Mexican hat potential. And this is a 3D illustration, and if we put it into 1D, it can be easy to understand. So the Lagrange is the equation of motions in this case, or we say it is the system itself. So we don't care about the details of these equations. What I want to say is that follow the simultaneous symmetry breaking, the result is the particle we input at first actually gained the particle without a mass we input actually gains masses from this mechanism. We call it Higgs mechanisms. So why is that? Because
What is mu?
I'm sorry,
What is mu?
mu. It's this part is the Lagrange's the equation of the Lagrange. Actually, I don't know what mu is here, but I can see that this equation actually it shows the system states. And the first part is referred to the kinetic term.
Yeah, that's what.
And the next part is the mass term. It's talking about the mass of these systems. So here, first we consider a particle without mass. So we deleted the second term.
Mhm.
And then we consider a potential energy that illustrates here. It's symmetric, right?
And so this potential energy with respect to sigma, sigma is space.
Mm-hmm.
It's like x, right?
Yeah, sigma is x.
Okay, so what is mu?
Mu.
What is the derivative?
Mu, I think it's like a coefficient of something like related to physics. So I didn't dig deep into this. I just want to show an example of a simultaneous symmetry breaking. And if you consider this potential energies and we say the origin at here, if you put a ball, the origin at here is actually unstable, right? So it will definitely fall into this place or this place. But when it falls into any one of these two, the whole illustration will be unsymmetric. So this is the simultaneous symmetry breaking. And by some mathematical transformations, you can find that at first we think this Lagrangian has no mass, right? But actually, when we translate the origin to the lowest energy state, for example, let's assume that the lowest energy fall into this. Well, okay. So if we like switch the origin from here to here and apply it into the Lagrange, and we found that the Lagrange in the end has the mass term in this case, and this part is like self interaction terms, and we don't care about it. So this is the Higgs mechanisms, a simple illustration of it. So
what you're saying is that
mhm.
when the frame of reference is moved, then the
It's
potential
like
energy
coordinate.
converts into something like mass.
Yeah. So actually,
That
this
is the symmetry breaking effect.
yeah, this is a way that some virtual particles can gain mass. Yeah, like quark or something else. So I mean, this is one of the results of simultaneous symmetry breaking. And if we consider 3D Mexican heads, we can see that for the first part, it is actually a discrete symmetry, right? It's a twofold symmetry, twofold reflection, right? But if we turn it into 3D physics, it can be a continuous symmetry. Because in this case, the lowest energy can either be here or here. But in this case, it can switch around this bottom of helios. So it's two different spontaneous symmetry breaking. First one is decreased, and next one is continuous. And here is the explicit symmetry breaking. It's quite easy to understand. For example, the external magnetic field. So basically, if we apply an external field, like either a magnetic field or electric field, it can induce a explicit symmetry breaking. Here is an example of the spectral lines of atoms. It's split in an external magnetic field in this case. So the first one is the Bohr model that everyone is familiar, but the next one is the Dirac model that consider external physics, what the spectral line will be. So it's called the Zeeman effect. So actually, what we are more care about is simultaneous symmetry breaking, because it has no external conditions and it is the origin of many physics phenomena. So here is the consequence of symmetry breakings. The first consequence is space group symmetry. So actually, space group symmetry is a broken symmetry, comes from the Euclidean group. Because the Euclidean group is a continuous spatial symmetry. But yeah. Okay, you got it.
I mean, but I will just say one thing. Like in your Mexican hat potential, the reason spontaneous symmetry breaking occurs is because you have a metastable state.
Yes.
Otherwise, it wouldn't. The energy minimization, when perturbed, will result in the ball going to the energy minimum.
Yeah.
Right. So that's why it's.
So that's why.
Which could be true for crystals too.
Yeah, that's why the simultaneous symmetry breaking is not always happened. So it depends on the potential, actually. Yeah. So the first one is space group symmetry. It comes from the symmetry breaking. And the second one is phase transition. For example, the cooling of a fluid into a crystalline solid is actually breaks the continuous translation symmetry. And the high temperature phase typically contains more symmetries than low temperature phase, because at high temperature, the phase, sorry. At high temperature, structures will become more disordered, right? Because of the thermal activation.
They have more entropic terms. That's
yeah.
what I mean. I don't think disorder is the right word there. I don't think you should call it disorder.
But in physics, I think they call it
entropy of mixing.
Entropy of mixing entropy. Yeah. Yeah.
I mean, it's like the disorder in nature.
Disorder.
Entropy, right? But I think what you mean is entropy. The probability of mixing is higher. If you go and rephrase everything, we're talking about disorder, what you really mean is mixing entropy.
Yeah.
Right? Even if you have potential, you say the entropy forces it to go away from metastable state into local state. So
yeah,
what you're really saying is the disorder is entropy. What do you mean here is entropy?
Yeah, right? Yeah. I think the entropy is the right physics definition. Quantity to describe this. Yeah.
Thermodynamically, that's the principle here.
Yeah.
Right.
So in phase transition, we have a specific parameter to describe the order of a phase. That is the order parameters. So actually, it parameterizes the extent of spontaneous symmetry breaking. So here are some examples. The first one is the ferromagnetic transition. It broke spatial rotation and autoplanar magnetic, and same as the ferroelectric transitions. The third one is the crystallization. It's like put structures from amorphous to crystals. It broke the Euclidean group, and its other parameter is actually the displacement and orientation. And the liquid to solid transition, it breaks the continuous translation. So the other parameter is density wave amplitude. What I want to say here is that the liquid solid transition, it breaks translational symmetry. It actually the result of spontaneous symmetry breaking. But liquid to gas transition, actually it has nothing to do with the spontaneous symmetry breaking. The other parameter for liquid to gas transition is actually the density itself. Yeah, and here we talk about the density wave amplitude, and we say that the phonos, or we say the vibrational modes in the crystal actually comes from the, we don't say density wave amplitude, we say the atom's fluctuation or disturbance in this case. So phonos actually also comes from the spontaneous symmetry breaking because it vibrates in its equilibrium state. So here we talk about the synthesizability. So here I categorize them into like 1, 2, 3, 4, 6 categories. And if we extend this, it can be very, very large. So there are so many things that we should take into consider. For example, the temperature, the pressure, or like the precursors, and some parameters that only works in some specific methodologies. So here comes the questions. The first one is if we want true property-driven or physics-informed material design. So I think it's not enough to just consider the space group symmetry of the crystals. So I actually think this the different types of generative models, actually they are trying to take the rules that take the laws that rule the real world into the model. For example, the equivariance is an example. And the diffusion models, or like flow matching, these two, we can tell from its name. So these models are actually simulating simulating the physics laws in this case. So the second one is how should these physics symmetries be incorporated into models? I think this is the hardest part. So if we really want to take into account symmetries besides space group, and what can we do in representation levels? Because I don't think we should focus on the model architectures that simulating the physics laws in this case. For example, to develop a new model architectures for a specific physics phenomena. So this is, I think, is important. And the third one is how to take the influence of external conditions on material synthesis or materials performance into consideration. Or for these external conditions that here shows, should it be parameterized or categorized? Okay, that's the end.
Yeah. No doubt that property, we need to look at external conditions. Question is whether it comes from data or representation. Interesting question to answer. Depends on the data set.
Yeah, that.
But how is this related to the symmetry breaking? We are thinking about like the property.
Because if we consider external conditions, we are actually consider explicit symmetry breaking in this case.
So property is explicit, and the crystal structure space group is spontaneous.
Yeah, I think.
I think that's correct.
Yeah. I'm not so sure.
But I mean, property doesn't always break symmetry.
Yes.
I mean, it could be like most properties come from linear approximation. They don't break in symmetry. So,
So
like for example, you go back to your ball picture. If you say my atom is going to sit at the energy minimum, and my property is only determined by some linear approximation around the ground state, there's no symmetry breaking. It stays in the local state, and then you can perturb it. This is the whole approximation of linear transport theory, linear everything. Highly nonlinear stuff, that would be correct. That's order transitions, like phase transitions are extreme. We're talking about very extreme things. If you're looking for those properties like phase transitions, metal insular transitions, amorphous, liquid to solid, then you're right. For small properties like magnetic response, electrical response, maybe electrocatalytic, maybe catalytic is not. Like you have to consider symmetry breaking, which might be true. Okay, thank you very much. Thank you, everyone. Super long. I think it's the longest group meeting we had so far. So far. All right. See you all next week. Bye.